Right now, you exist in 3 dimensions. You can move left and right, up and down, forward and backward. 3 directions. That's all you need to describe where anything is in a room. But the AI running on your phone right now doesn't live in 3 dimensions. It lives in 1,000, sometimes more. GPT processes every sentence in a space with 1,500 dimensions. Image models work in spaces with tens of thousands, and that's not a flaw or a hack. There's a deep mathematical reason why high-dimensional spaces are exactly where machine learning works best. Why AI lives in 1,000 dimensions. Before we get into the weird stuff, let's make sure we agree on what a dimension actually is. It's simpler than it sounds. A dimension is just a number, a single measurement. If all you know about something is its weight, that's one dimension. One number, one axis. If you know its weight and its height, now you need 2 numbers to describe it. 2 dimensions, a point on a flat plane. Add depth and you're in 3 dimensions. 3 numbers, 3 axes, 3 dimensions. This is the world you're used to, but data doesn't stop at 3. A photograph that's 1,000 pixels by 1,000 pixels has 1 million brightness values. That's 1 million dimensions. A sentence fed into ChatGPT gets converted into a vector with 1,536 numbers. That's 1,500 dimensions. Even a song on Spotify is described by 128 audio features, 128 dimensions. Every measurement you make adds a dimension, and modern AI makes a lot of measurements. Let me show you exactly how this works. Take a tiny 5 by 5 image. Each pixel has a brightness value, just a number between 0 and 255. Now flatten that grid into a single list. You get 25 numbers in a row. Congratulations, that image is now a point in 25-dimensional space. That's what a vector is, just a list of numbers that represents a position. Audio works the same way. Sample a sound wave at regular intervals, and you get a list of amplitudes. Each sample is a dimension. Text is the most interesting one. In modern language models, each word or piece of a word gets converted into a dense column of numbers. In GPT, every single token becomes a vector with 1,536 entries. Not a word, a point in 1,500 dimensional space. So when people say AI understands language, what they actually mean is that it has learned to place words at useful positions in a very high-dimensional coordinate system. So data lives in high-dimensional spaces. Why does that matter? Because high-dimensional spaces behave in ways that completely break your intuition. Here's the first weird thing. In 2 or 3 dimensions, when you scatter points in space, some are close and some are far. The distances between them are all over the place. You can instantly tell which point is your nearest neighbor. But watch what happens as we increase the number of dimensions. At 10 dimensions, the distances start bunching together. At 100, they are noticeably tighter. And at 1,000, every single point is almost exactly the same distance from every other point. The nearest point and the farthest point are practically the same distance away. This is called distance concentration. The mathematical statement is that the ratio of the maximum distance to the minimum distance approaches 1 as dimensions increase. The variation between distances shrinks to nothing, and this means that in high dimensions, the very idea of closest point starts to fall apart. Here is another way to visualize it. This histogram shows every pairwise distance between 100 random points. In 2 dimensions, you get a wide spread. As dimensions increase, the distribution narrows. At 1,000 dimensions, it collapses into a single spike, one distance. Everyone is the same distance from everyone else. Welcome to high-dimensional geometry. Here is a related effect that is equally strange. If you scatter random points inside a circle in 2 dimensions, they fill the whole area, points everywhere, center, edges, in between. But in high dimensions, something different happens. Almost all the volume of a high-dimensional sphere is concentrated in a paper-thin shell right at the surface. The interior is essentially empty. It's like all the water in a swimming pool, migrating to within a millimeter of the walls. Nothing in the middle. Now the second phenomenon. Take 2 random vectors, just 2 random arrows in space. In 2 dimensions, the angle between them could be anything. 15 degrees, 90 degrees, 150. But in high dimensions, something remarkable happens. The angle snaps to 90 degrees, every pair. No matter which 2 random vectors you pick, they are always approximately perpendicular. And there is a clean mathematical reason for this. The angle between 2 vectors depends on their dot product, which is just the sum of multiplying corresponding components together. Each component product is random, sometimes positive, sometimes negative. When you only have a few terms, the sum could land anywhere. But with 1,000 terms, you are adding 1,000 random positives and negatives. The law of large numbers kicks in, they cancel almost perfectly, the sum lands near 0. And when the dot product is 0, the angle is 90 degrees. In 1,000 dimensions, random vectors are almost mathematically guaranteed to be perpendicular. Think about what this means practically. In 2 dimensions, you get 2 independent directions. In 3, you get 3. In 1,000 dimensions, you have 1,000 directions that are all mutually perpendicular, 1,000 independent axes. That is an enormous amount of room to organize information. And this is the key insight. This is why AI uses so many dimensions. Not because it is wasteful, but because each dimension is a new direction to encode something distinct. 1,000 dimensions means 1,000 independent features, all without any of them interfering with each other. Now there is a flip side. High dimensional spaces have a property that is genuinely problematic. In 2 dimensions, a circle fills about 79% of the square around it. In 3 dimensions, a sphere fills 52%. By 10 dimensions, a hypersphere fills only a quarter of 1% of its bounding cube. And at 100 dimensions, it is effectively zero. Almost all the volume is in the corners. The center is empty. This is called the curse of dimensionality. Data becomes incredibly sparse. Sampling the space uniformly becomes impossible, and many classical algorithms designed for 2 or 3 dimensions completely break down. But here is the twist. That same property that makes some things harder makes one thing dramatically easier. Classification. Imagine you are trying to separate 2 types of data. With only 2 features, the clusters overlap. No single line can cleanly divide them. But add more features, add more dimensions, and the clusters pull apart. Each new dimension gives the data a new direction to separate along. By 10 features, there is a clean gap between the groups, one straight line, perfect classification. This idea is formalized in Cover's theorem. As the number of dimensions grows, the probability that any random labeling of data becomes linearly separable approaches 100%. More dimensions do not just help, they make separation almost guaranteed. This is the blessing of dimensionality, and this is the fundamental trick that neural networks exploit. Here is the classic example. The XOR problem. 4 points, 2 colors, red at opposite corners and blue at the other two. In 2 dimensions, there is no straight line that can separate them. It is geometrically impossible. But the neural network does not try to find a line. Instead, it learns a transformation, a smooth warping that bends the 2 dimensional plane into a 3 dimensional surface. A saddle shape, and now a single flat plane cuts perfectly between the red points above and the blue points below. The network did not change the data. It did not change the labels, it changed the geometry of the space. It lifted the data into a higher dimension where the answer became trivial. Every layer of a neural network performs one of these transformations. Data comes in at 1 dimensionality, gets projected into a different dimensionality, and comes out the other side, 3 dimensions in, 6 in the hidden layer, 2 dimensions out. In real models, the numbers are much bigger. Each transformer layer in GPT takes hundreds of dimensions, projects them into thousands, giving the network room to mix features and find patterns, and then compresses them back down. This happens dozens of times. Layer after layer, the model repeatedly expands into high-dimensional space and contracts back, refining its understanding each time. And this is not abstract theory. Every single word you type gets converted into exactly this kind of vector. The word king becomes a list of numbers, a position in a space you cannot visualize, but the math can navigate perfectly. And here's the part that still feels like magic. In that space, relationships between words become geometric relationships. The direction from man to king is the same direction that takes you from woman to queen. King minus man plus woman equals queen. That is not a metaphor. That is literally what the vectors do. Meaning itself becomes geometry. Directions and distances in a 1,000 dimensional space. And this geometry is useful in a very concrete way. Every time you search for something, an image, a song, or a document, the system converts your query into a vector. Then it measures the distance from your query to every other stored vector. The closest ones are the most similar results. This is how image search works, how recommendation engines work, how retrieval systems in modern AI work. You are not matching keywords. You are finding the nearest points in a geometric space. And the reason it works so well is precisely because of all the properties we talked about. Distances concentrate, vectors become orthogonal, data becomes separable. High-dimensional space is deeply unintuitive. Humans evolved in 3 dimensions, and our brains never needed to understand what happens in 1,000. But the math does not care about our intuition. In 1,000 dimensions, there is enough room for 1,000 independent ideas to coexist without interfering with each other. Enough structure for patterns to emerge that would be invisible in lower dimensions. Enough geometry to turn the mess of language, images, and sound into something a machine can reason about. That is why every major AI system works in high-dimensional vector spaces. Not because engineers ran out of simpler ideas, because this is where the math actually works. High dimensions are not the problem, they are the solution.